Hello everyone, once again. This is the second attempt of SpaceX Falcon 9 to be launched together with the NanoAvionics spacecraft Charlie, which was built for our customers Aurora Insight. Yesterday it was postponed due to bad weather conditions, and we hope today it will get up. Arnold, maybe you want to give a few words about the mission, so we recap.
Yep, so Charlie's mission is basically to quantify the radio frequency spectrum across the globe. Charlie mission is a 6U satellite, which is built and designed by NanoAvionics. 6U is basically a CubeSat standard satellite of the size of 10, 20 to 30 and 30 centimeters. The satellite will be deployed in a low Earth orbit, 530 kilometers. It will also have the inclination of 97.4 degrees, so basically being sun-synchronous orbit, which means that the satellite's orbital plane has a constant angle with the sun. The satellite's orbit period will be around 1 hour 35 minutes, of which 40% of the time satellite will spend in the eclipse and 60% of this time it will spend in sun. The foreseen mission lifetime is around 5 years, so we will have good 5 years of operations, and after that the satellite will decay naturally.
You saw briefly a short video about NanoAvionics, what we do. So just in short, in summary, so we are a nanosatellite mission integrator and providing a solutions for such companies as Aurora Insight to implement the missions. Jennifer, would you like to tell something more about the Aurora Insight?
Yeah, certainly. Thanks, everybody, and welcome to today's event. We're so excited to have you here. It's an important day for our company. We're launching our Charlie satellite, and the Charlie satellite is carrying a satellite payload. That's our most advanced payload that we've ever built. The payload is actually a sensor, and the sensor measures what's called the radio frequency spectrum. We'll talk a little bit more about the radio frequency spectrum later, but in short, Charlie is going to create for us some amazing data. And with this data, we'll be able to provide information to companies across the world that will help them improve communications and connect more people. So thank you for joining us today for this exciting event.
Thank you, Jennifer. Just a side note for our teams who watches this live stream, comments are welcome in our Facebook page. And if we will have a time, we will try to answer as many questions as we can for today. Also, for a few times, we already mentioned the name Charlie. Maybe someone from Aurora team can explain us why it is Charlie, how you came up with this name.
This is Gus. And, we as a company knew we would be successful and knew we would be launching a long string of spacecraft. And since we are a communications company, we collect data for communications companies and improving it. We wanted to use something that reflected that notion. So we went to the NATO alphabet that makes communication more clear between people. And so we started with Alpha. Our first spacecraft launched at the end of 2018, beginning of 2018. We are stepping through that. But of course, this is space. And so our Charlie spacecraft is launching before our Bravo spacecraft.
All right, thanks. So it sounds like we have a chance for a long-term collaboration if we need to cover all the alphabet. Cool. Thank you. Arnoldas, can you help to understand a bit better what is this satellite, 6U satellite, for our general public?
Yep, cool. So let's jump to the technical part of the Charlie satellite itself. So Charlie satellite is based on the NanoAvionics built, designed, and manufactured M6P, so multi-purpose 6U platform. The 6U name stands for the size of the satellite, so basically it is following the CubeSat standard. The CubeSat standard defines the 1 unit, or 1U, as 10 by 10 by 10 centimeters. So of course the M6P is 6 units, so it's 10 by 20 by 30 centimeters. Or to visualize it better, you can imagine the size of a shoebox, so it's comparable that way. Of course, to reach the mission success and to reach all the Charlie's and Aurora Insight's goals, the satellite is integrated with variety of functions and subsystems. I'll cover these later, a bit later in the broadcast, but basically the Charlie satellite has the capability to generate the power and distribute it to the all onboard avionics, as all the electronics need some power to be generated with. Altitude control system, so because the satellites need to point to particular directions in the Earth if there's some sort of area of interest, so the Charlie satellite has that as well. Of course, it has onboard computers, which allows us to have a bit of autonomy because the satellite passes over the ground station only 5 to 6 times per day, so the onboard computers allows us to run some tasks automatically. And also to send the commands to the satellite and receive the commands and receive the data from the satellite, we have onboard communication radios, which I'll cover a bit later. Now I think it's a good time to cover the basically the launch schedule and talk about the orbital parameters where the satellite will be launched with. So Charlie satellite will be launched on Falcon 9 Block 5 B1058-5 rocket. It's actually the last iteration of Falcon 9 rocket. It's being launched for Cape Canaveral in Florida, United States of America. Some interesting facts on the rocket itself. So the rocket is 70 meters tall. It produces around 8,000 kilonewtons of thrust, so that's basically more than 5 Boeing 747 aircrafts at full power. The payload mass on this rocket is around 5 tons, so 50 baby elephants, or 1 big elephant. And this rocket is actually carrying a record-breaking number of satellites, so 143 satellites, so we're being part of history here. So 10 of those satellites are, of course, Starlink, and 1 is NanoAvionics built Charlie satellite. Some other interesting facts. The first stage that is used on this rocket will be reused for the 4th time. The last mission that it was used for was Dragon 2 mission. It was a manned mission to International Space Station. Let's not forget, of course, the other goals of the rockets besides launching the rocket itself and deploying the satellites. As typical for SpaceX, they will try to recover the first stage. The first stage will be recovered by a autonomous spaceport drone ship. Of course, I love you. And it's expected to foresee that the fairings will be caught as well. This is planned, and the vessels that they will be caught on are Mrs. Go Tree and Miss Go Chief. But we will see later on what are the plans with the SpaceX. Now a bit the orbit. So the Charlie satellite will be launched in a low Earth orbit, or shorter LEO, 530 kilometers from the ground surface. The inclination, basically the angle of the orbit, is a 97.4 degrees. It's called a sun-synchronous orbit. Sun-synchronous orbit, or SSO for short, basically says that the satellite's orbital plane has the constant angle with the sun. In general, the LEO orbit is the most popular orbit in the industry. So we currently have around 3,000 satellites flying in space, and half of that is flying in low Earth orbit. The reason for that being that you need least amount of energy to put those satellites in space. A bit more on the orbit. The orbit period is around 1 hour 35 minutes. 40% of that time the satellite will spend in eclipse, and 60% of the time the satellite will spend in sun, where it will be able to generate the required power. The orbital velocity of the orbit is 7.59 kilometers per second. So within 24 hours, the satellite will rotate the Earth around 15.4 times. And of course, to meet the ESA, the orbiting requirements, the satellite, due to the atmospheric drag that is in space, will deorbit within 5 years. So that gives us 5 good years of Charlie satellite operations. A bit more about the launch scenario here. So the launch is foreseen at 2:40 UTC. But we do have a 42-minute launch window. In between that 42 minutes, the launch can be postponed, but hopefully that does not happen, and we follow the schedule. Weather currently is 60% to go. And after the launch, we'll have around 10 minutes before the first stage landing, and then 59 minutes once the first satellites are being deployed. So as I said, more information will be given by SpaceX when we join their stream. And now I'll give the floor to Žilvinas.
Yeah, so it's actually about the time to join the SpaceX live. Before we join there, I would like to say thank you for our colleagues from ExoLaunch who helped us with the integration in US to the final checkouts with the spacecraft. And I see that we have already live stream from the SpaceX. So let's join it to see it. Fingers crossed, we have a successful liftoff.
LWO1 WeatherNet. Liftoff conditions looking pretty good.
ESTS is ready for launch. Ignition. Liftoff.
Falcon 9 has cleared the tower.
Ten, 9, 8,
Side booster ignition.
6, 5, 4, 3, 2, 1.
Good morning. It's Sunday, January 24th, and we're here at SpaceX's headquarters in Hawthorne, California. You're looking at a live view of Falcon 9 as it awaits its 10 a.m. Eastern Time launch from Cape Canaveral Space Force Station in Florida. My name is Andy Tran, and I'm a production supervisor here at SpaceX. Welcome to the webcast for SpaceX's Transporter-1 mission. It's our first dedicated small-sat rideshare program launch and third launch of 2021. If you joined us yesterday, you know we scrubbed for weather specifically for the surface electricity field rule. Today's weather has also been a bit challenging, but we're currently looking good for our T0 liftoff time. On board this mission are 133 commercial and government spacecraft, in addition to 10 Starlink satellites, the most spacecraft ever deployed on a single mission. This count includes CubeSats, microsats, and 2 orbital transfer vehicles, sometimes called space tugs, which will deploy their spacecraft after separating from Falcon 9. SpaceX created the SmallSat rideshare program to provide small satellite operators with competitive pricing, increased flight opportunities, flexibility, and most importantly, a ride to space on SpaceX's Falcon 9, Falcon Heavy, as well as Starship in the not too distant future. For more details on our rideshare program or to reserve your spot, head over to our website at spacex.com/rideshare. Now let's take a look at Falcon 9 out on the pad at the Cape. You're looking at a live view of Falcon 9, our 70-meter, 2-stage liquid fueled launch vehicle. Today's mission is the 5th flight for this particular booster. Its first 4 flights were all in 2020, which included our Crew Dragon Demo 2 mission for NASA in May, the Anasis 2 mission in July, a Starlink mission in October, and most recently, CRS-21 in December. You can tell by the re-entry soot at the bottom of the vehicle that this booster has flown before. That bottom 2/3 of the vehicle is the first stage. Its objective is to accelerate the vehicle through the Earth's atmosphere into space and then separate from the rest of the rocket. From there, it will make its way back to Earth and target a landing on a recovery vessel. Of course, I Still Love You. There she is on screen. On top of the first stage is the black carbon fiber inner stage. This composite material houses the larger nozzle of the second stage engine. And then on top of the inner stage is the Falcon 9 second stage, which will take the payload to its eventual destination in orbit. After the first stage separates about 2.5 minutes into flight, the second stage will then carry the 143 spacecraft to orbit. In order to get to the intended orbit today, we'll need to light our second stage twice before deploying all of our payloads. And at the top of the rocket, you'll notice a large nose cone. This is called the fairing. It's a composite structure and protects the rocket from the forces of ascent and also houses our payloads. Once the vehicle is outside of the Earth's atmosphere, the fairing separates to expose the satellites to space. For today's mission, both fairings halves are brand new, and our recovery vessel, Miss Chief, will be attempting to recover the fairing halves from the water following landing. And finally, the large truss structure next to Falcon 9 is called the Transporter Erector. We also refer to it as the TE. Its job is to roll Falcon 9 out to the launch pad, raise it to a vertical launch position, and also route power, fluids, and communication to the rocket and satellite. It will retract away from the rocket slightly around the T-minus 4.5 minute mark, providing clearance for Falcon 9 to lift off. The chief engineer held a technical poll at the T-minus 1 hour mark, and the launch director held a propellant load and launch go-no-go poll at the T-minus 38 minute mark. Weather is still tracking to be green for a T0 liftoff. Falcon 9 has been loading propellants since the T-minus 35 minute mark. The vehicle uses a refined form of kerosene called RP1 for its fuel and super chilled liquid oxygen, or LOX, as its oxidizer. Currently, RP1 is fully loaded on the second stage and nearly fully loaded on the first stage. Liquid oxygen is currently loading and currently underway on both stages. As for helium, it began loading before the webcast went live and will continue to top off until about 1.5 minutes before launch. We use helium as a pressurant as the propellants are pulled out by the engine pumps. In about a minute, around T-minus 7 minutes, engine chilling will begin. This is where we allow a small amount of super chilled liquid oxygen to flow into the Merlin engine turbo pumps prior to the full flow of LOX to avoid any thermal shocks to the system. Checkouts of the second stage thrust vector control actuators will also be underway. This is known as the engine wiggle test. We move the thrust chamber slightly to make sure that the guidance hardware is a go for flight. The first stage actually does the same test, but it happens just seconds before ignition. So far, the vehicle is healthy. We are currently working no issues. The range is standing by and currently green for launch. And again, weather is a tracking item, but right now we are green for T0 liftoff time. We are currently 7 minutes from liftoff. Falcon 9 is now moving into the final stages of the countdown. In about 2 minutes, the transport erector will start to retract away and enter its pre-launch position about 2 degrees from the rocket. At liftoff, hydraulics will move it to a position about 45 degrees away from the rocket. Again, around the T-minus 4.5 minute mark, you'll hear some hiss and pop, and that's pressure venting from the rocket and the plumbing of the transporter erector. The vehicle remains in good health. We're continuing to load propellant on both the first and second stages. You can see that we've had some gaseous oxygen venting from Falcon 9. About a minute before liftoff, you'll hear the announcement that Falcon 9 is in startup, which means that the rocket's own internal flight computers are now autonomously controlling the launch countdown. The payload inside the fairing halves continue to be healthy. The Falcon 9 team is tracking no issues on the rocket. Weather, again, is a tracking item for us, but currently we're green. And as a reminder, if we don't launch today, we'll make another attempt sometime in the future, and we'll let you know as soon as we know that date. And as I mentioned earlier, today's launch is the first of SpaceX's dedicated smallsat rideshare program, which provides small satellite operators with competitive pricing and increased flight opportunities on board the world's most advanced and proven launch vehicles. As part of the program, we also offer traditional rideshare opportunities on existing low Earth orbit missions and on SpaceX's Starlink missions, which launch about once a month. Traditionally, it's pretty hard to find affordable space on a rocket for a small satellite. Our rideshare program groups small sats together, making it easier to purchase a less expensive ticket to orbit on a predictable schedule. And unlike traditional rideshare opportunities, our rideshare missions are not dependent on a primary payload. Our missions are pre-scheduled and will not be held up by delays with co-passengers. So that means that if you're ready to fly during the scheduled launch period, you will fly. Since we announced the program, we have launched 4 rideshare missions, including 2 Starlink missions with Planet on board, 1 Starlink mission with spaceflight riding along, as well as the Falcon 1B mission. And in fact, one of these customers flew less than 6 months after they contracted with SpaceX, which is a pretty remarkable turnaround time. We're really excited for today's mission, not only because it's the first dedicated rideshare, but because it will also be the most spacecraft ever deployed on a single mission. As I mentioned earlier, in addition to the more than 130 small satellites on board for our commercial and government customers, we have 10 Starlink satellites of our own riding along. And as many of you may know, Starlink is a constellation of satellites that can provide high-speed, low-latency internet all over the globe, particularly in remote or rural areas where connectivity is limited or completely unavailable. The 10 Starlink satellites launching aboard this mission will also be the first Starlink satellites deployed to a polar orbit, and many of the future Starlink sats flying to the polar orbit will actually launch from our Vandenberg site here in California. The Vandenberg team is hiring for a number of open positions to support our growing operations there. If you're interested in working on the launch team that will help all kinds of payloads launch from our West Coast facility, head over to spacex.com/careers and apply. We are about 3 minutes from liftoff. Falcon 9 is moving into the final stages of the countdown. The payload and vehicle remain healthy, and we're still currently tracking weather to be green for a T0 liftoff at 10 a.m. Eastern. In about 30 seconds, around the T-minus 2 minute mark, we should finish liquid oxygen loading, and that will wrap up the final propellant loading for Falcon 9. For those just joining us, this is the Transporter-1 mission for SpaceX, the 3rd launch of 2021 and the first dedicated small-sat rideshare mission for SpaceX. And we just heard the call that LOX loading is completed. Again, that is the last of propellant loading for Falcon 9. And on screen, you can start to see some white clouds forming around Falcon 9. That is normal and expected for us at this stage in the countdown. That is liquid oxygen condensing as it meets the warmer ambient temperatures of the Florida air.
Falcon 9's in startup.
And the vehicle is in startup. Both stages are beginning to pressurize for launch. In a few seconds here, we should be hearing the launch director give the final go for liftoff.
LD on countdown 1, go for launch.
And there you heard it. That is the final go for launch at T-minus 35 seconds. All systems are go for the Transporter-1 mission. Let's listen and watch in as we lift off from Cape Canaveral Space Force Station in Florida.
T-minus 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition and liftoff.
Impulse pitching downrange.
Stage 1 chamber pressure is nominal.
We are T plus 43 seconds into flight. Falcon 9 has cleared the tower and is currently throttling down to prepare for max Q at around the T plus 1 minute and 12 second mark. Max Q is where the vehicle will experience the highest amount of aerodynamic pressures.
Falcon 9 is supersonic. Max Q.
And we've just passed max Q. That is a really cool tracking shot of Falcon 9. All is looking good with the stage 1 trajectory. In about a minute, we have 3 events coming up in quick succession. First up is main engine cutoff. That's where the 9 engines on the first stage will shut off, followed by stage separation, where the first and second stages will separate from one another. Shortly after that, we'll have second engine start 1. The Merlin vacuum engine on the second stage will ignite its engine and continue its journey into orbit.
MVAC engine chill has begun.
We're about 20 seconds away from main engine cutoff, the start of those 3 events happening in rapid succession.
Main engine cutoff.
Stage separation confirmed.
Coming up in a few seconds, we should have the fairing deploy.
MVAC ignition.
Fairing separation confirmed.
And there you can see the 2 fairing halves have separated and fallen away from the vehicle, exposing the 143 spacecraft to the vacuum of space. And as a reminder, our recovery vessel, Miss Chief, will be attempting to recover the fairing halves today from the water. We're at T plus 3 minutes and 30 seconds into flight. We have a couple of views on screen right now. On the right-hand side is a view of the second stage, specifically the MVAC engine. It's currently in the first of its 2 MVAC burns. This burn should last for about another 5 minutes or so. And on the left-hand side of the screen is a view from the top of our first stage looking down. The next milestone for the first stage will be its re-entry burn. Falcon 9 needs to execute an entry burn to slow itself down before hitting the dense parts of the atmosphere. Without this burn, relying on the atmosphere alone to slow Falcon 9 down will put unnecessary strain on the rocket. And that entry burn is coming up at around the T plus 7 minute and 47 minute mark, just a few minutes from now. For those just joining us, this is the Transporter-1 mission for SpaceX, the first dedicated small-sat rideshare program mission, and it's also the third mission of 2021. We're just waiting on the next major event for this mission, which is the first stage entry burn. That's going to be happening around the T plus 7 minute and 47 mark. You can see some periodic bursts of gas from the first stage. That is nitrogen from our attitude control systems. They help to orient the first stage as it continues to make its descent back towards Earth. And as we get closer to the Earth, you'll start to notice those honeycomb-like structures on the left-hand side of your screen start to move and pivot. Those are our hypersonic grid fins, and those help to steer the first stage back as it returns back to Earth. As for the second stage, impact performance looks nominal. Just a few seconds after we finish the stage 1 entry burn, we'll be shutting off the second stage Merlin vacuum engine and enter a small coast phase. Again, we'll need to relight this engine later on in the mission to get to our eventual destination in orbit.
Stage 1 FTS is saved.
We are about 45 seconds away from that stage 1 entry burn. For the entry burn, it is a 3-engine burn, so 3 of the 9 Merlin engines on the first stage will relight and start to slow the stage down before it hits the denser parts of the Earth's atmosphere.
Stage 1 entry burn startup.
And there's the entry burn. 3 of the 9 Merlin engines have relit. This burn is expected to last for about 30 seconds.
Second stage and terminal guidance.
Stage 1 entry burn shut down.
And you can see on screen the entry burn has concluded, and in just a few seconds we should be hearing the call out for second engine cutoff, where we'll shut down the second stage MVAC engine.
FTS is saved.
There's the second stage.
Also signal stage 1, Cape expected.
The second stage has shut down its engine. Now, as I mentioned earlier, we are going to be attempting to recover the booster for a 5th time.
Nominal parking orbit insertion.
On our drone ship, Of Course I Still Love You. The first stage has 1 more burn left, the landing burn, and it begins just before we touch down and provides the booster with a soft descent before we land. That should be starting up anytime now. And we did get confirmation of the second stage that it did reach a good parking orbit.
Stage 1 landing leg deploy.
LOS stage 2, Cape Canaveral expected.
And Falcon 9 returns safely once again. That is the 5th time for this particular booster and the 73rd recovery of an orbital class rocket. A great way to start off the mission and a great way to start off the Sunday. We're now going to coast for the next 45 minutes or so while we wait for SES-2 or second engine start number 2. We're going to leave you with an animation that shows you where we're at in the coast phase, and we'll see you back here at the T plus 54 minute mark.
Welcome back to our studio. We just saw the successful liftoff of the Falcon 9 launch vehicle, and we're going to the orbit. So it's a great achievement for the both teams, NanoAvionics and Aurora Insight. Round of applause goes to you, all guys. Now we will have some time until the launch vehicle will reach the right orbit for the deployment. And in the meantime, we would offer you to see Q&A from yesterday's live event we had with the Aurora Insight. So you will be able to learn both technical and business insights of this specific mission. And we will come back to our studio just before the deployment sequence will start, so we can witness the deployment itself together. So let's just explore what does Aurora Insight do, and what are your objectives as the company with your services.
Thanks, guys. Yeah, I'd be happy to talk about Aurora Insight. So ultimately, we want to help more people around the world be connected through wireless communication. And, you know, we're all familiar with wireless communication. We have our smartphones and our Wi-Fi and Bluetooth devices. And of course, wireless signals that are carrying information can't be seen. But we've developed some pretty incredible technology that can measure these wireless signals. And the wireless signals that we're measuring are part of the electromagnetic spectrum called the radio frequency spectrum. This is a very important aspect that we can measure the radio frequency spectrum, and I'll explain that by using the analogy of land. So land, well, you're not making any more of it. There's only so much of it, so it's a finite natural resource. And it's also very valuable because it has so many uses and it's finite. So similarly, the radio frequency spectrum is a finite natural resource, and it is valuable. And in fact, just a little bit ago, earlier in January 2021, the FCC auctioned off this tiny sliver of radio frequency spectrum to telecommunications companies. This tiny little sliver of spectrum raised over $81 billion. So you can see that spectrum is very valuable. Well, as a scarce and valuable natural resource, we need to understand how it's being used, where it's being used, what it's being used for. And this is the same for any natural resource. We have to be able to use it wisely, to use it efficiently and effectively. Well, that's where Aurora Insight comes in. We measure the radio frequency spectrum. And with these measurements and some pretty incredible processing, we are able to create analytics and insights that provide a new view on how the radio frequency spectrum is being used. And this information is used by our customers across the wireless industry, across the globe, to improve wireless communications and expand their networks. So Charlie's carrying our most advanced payload to date, and we're so excited to see what it'll produce when it's finally launched tomorrow.
Okay, thank you, Jennifer. Also, I want to ask one question so we understand the value of RF monitoring, but how the results that you will get from the Charlie mission and from the upcoming missions will help the businesses and industries all across the world.
So Aurora Insight, we serve a bunch of different wireless industry verticals, governments, et cetera. And those range from wireless service providers to tower companies, people who manufacture equipment to make wireless networks work, the wireless equipment manufacturers, and the users of wireless technology, and in the end, anybody that's investing in the wireless ecosystem, period. So our insights sort of offer them the opportunity to optimize these investments. There's no industry right now that is not impacted by wireless technology. There's trillions of dollars will be spent on it over the next decade, especially as 5G starts to roll out and we look towards IoT technologies. So the businesses that make the best use of wireless technology and the governments that best manage it will be the most successful ones. So just for the wireless services industry, meaning the carriers that you use every day for your cell phone, whether you be in Lithuania or in the United States, they need opportunities to better deploy their networks. Again, they're going to spend trillions of dollars over the next decade to make these networks work for their customers. And so as they place their infrastructure, as they buy their equipment, if they're not doing it efficiently, they can waste a lot of money. So our goal is to provide them with the information that allows them to get ahead of their competition and save a lot of money and make better investments along the way.
All right. Thank you. So if you summarize from everything what your colleague said, there is a lot of importance in all the networks, and in one way or another way, we are surrounded by the different frequencies with different radio waves. They are kind of invisible, untouchable, but people do talk about those, right? Someone are scared of those, but maybe you can tell us a bit more what the radio frequencies, radio web effect will have in our day-to-day life.
This is Greg. Our new satellites continue to push the boundaries of commercial radio frequency sensing. Our telecom-centric customers are asking for more answers over every region of the Earth. And in our modern world, where virtually everything is wirelessly connected, our next-gen satellites are key to supplying germane and timely RF geospatial insights. And therefore, in a global market void of ubiquitous spectrum and RF intelligence, we're eager to further support investment decisions, quality of service, and regulatory advocacy.
Thank you.
Thank you, Greg. So looking more a bit into the future, we all know that for global coverage in LEO orbit, we need a bigger number of satellites. So talking about that, can you give us a bit more details of your future space-based infrastructure?
Sure. So as we've already touched on previously, Aurora Insight's space-based infrastructure, it consists of a growing number of nanosatellites, the second which will actually be launched tomorrow now. So each of these satellites, they've been developed to include a custom sensor on board, and that allows us to observe the radio frequency environment while the satellite is in orbit. Satellites make an ideal platform for our sensors because they allow us to survey the entire globe every single day. And in the future, we expect that we'll be continuing to improve the sensor that we have on board. This sets our satellites apart from traditional means of radio frequency sensing, where you need either drive or fly your sensors to the areas you're interested in. And this allows us to get real-time insights to the radio frequency environment on a global scale in the future. I mentioned this is the second satellite that we've launched, but we have plans, as we've discussed, to continue growing our satellite network into the future. This is going to allow us to get more frequent and more fine-grained observations as we continue to grow this network about the radio frequency environment from space.
Okay, thanks, Ben. So as all we understand, Aurora Insight is developing the instruments, right, which are capable of tracking and monitoring the frequencies from space. Brent, would you like to join and tell us a bit more how NanoAvionics contributes to these nice business applications?
Well, in general, NanoAvionics started about 6 years ago in Lithuania and developed a core vertically integrated set of subsystems that played together well and could be reconfigured per each individual customer's needs without too much NRE, making it very adaptable. It can be done in a short period of time and meet the needs without having every customer pay for too much that they don't need. So our main goal here with Aurora Insight was to make sure that we could support their business case, to give them access to space with their instruments to do their business in the most cost-effective way ever. So that's what we did with our very adaptable infrastructure based on CubeSats and nanosats.
All right. Thank you, Brent. So I guess another point I would like to touch is a bit to describe maybe the scope of work, if we can call it like so, what we did with the Aurora Insight, or what was delivered from NanoAvionics side for this specific mission. And we are very grateful that Aurora team selected NanoAvionics to provide the full mission integration services, which mean that we manufactured the spacecraft, we did all the payload integrations in our facilities. We did all the environmental testing campaigns. We were allowed also to arrange the launch for them. Unfortunately, it's not happening today. It will happen tomorrow, and one more in upcoming months. We're also working together with our ground station network providers, so we can provide as much data from space back to ground as possible. Again, to improve and give more speed for this business case, right? To get as much data as possible. In addition to that, we also use several new space, let's say, approaches, how we can make these things happen quite fast. Because everything happened since we began to work not in a full year until we were ready for launch. Our customer also had the chance to use the flat-set, so-called virtual satellite, where they can early on start developing the payload, and we can be ready for integration, and integration will be very smooth because we tested quite a lot beforehand and getting the actual payload into our facilities. And then this leads me to another point. Actually, we had 2020 was quite difficult year for everyone, right? We're not complaining because we have achieved quite successful results all together and together with the Aurora team. So my question would be, maybe Aurora team has some comments or let's say insights on what makes such partnerships, successful, even though we're having such kind of difficult times, right?
I think the major thing that made us successful was our communication, and I'm going to take a little bit of time to walk through the process that enabled us to get this project completed in just over a year. As you mentioned, 2020 was a difficult year for many reasons, and starting in March, we were unable to travel around the US and to Lithuania with our sensors. That made us perform most of this project remotely. Just on the Aurora side, we have team members on this project in 6 different states: Colorado, Utah, Michigan, Massachusetts, Maryland, and Virginia. And so the limited office access and hardware availability really impacted our process. However, we managed to complete the hardware design, manufacturing, assembly, software development, testing, mission planning, and documentation, like I said, in just over a year. And that was really based on the detailed communications we had with NanoAvionics and their really stellar documentation. There are a few team members on Aurora that I want to call out who are really involved and instrumental in this. In addition to those you've heard from today, Earl Coe, Don Wichern, Yunki Park, and Anush Khan, they all were instrumental in getting our sensors built and shipped to Lithuania and tested once they were there. Once our sensors arrived in Lithuania at the NanoAvionics facility, we've been very impressed with their level of time and effort understanding our payload throughout the integration and testing process. There were a few minor issues, but overall the INT process was very smooth thanks to their hard work. And additionally, they set up and maintained a full benchtop setup for us to integrate with an engineering model payload. and test our software and hardware integration. Unfortunately, we didn't launch today, but we're incredibly proud of this achievement, and we're really excited to looking forward to our first data from Charlie on orbit and continuing our work together with NanoAvionics for the foreseeable future.
Thanks, Josiah. So I guess if we cannot cheer up for the successful launch, so at least we can shoot out for both engineering teams doing amazing job in this time frame and being ready to launch. So congrats to Aurora team and congrats to all NanoAvionics engineering team who made us to be where we are today. And then I guess we can move a bit to discuss about the Aurora spacecraft, the Charlie itself, how it technically was designed, and I will give a floor for Arnoldus.
Yep, thank you, Žilvinas. So as previously promised, I will cover a bit about the NanoAvionics satellite buses and the Charlie satellite as well. So here on the desk we have the standard M6P platform. Behind me you can see here the actual Charlie satellite that hopefully will fly tomorrow. So first things first, 80% of avionics that we put in our satellites are manufactured and designed by NanoAvionics. So that helps us to get a very quick turnover when it comes to high quantities of satellite production. Other thing is that the avionics that are used in the 6U satellite can be used in smaller or bigger satellites. So, for example, the onboard computers or the reaction wheels that are used in the Charlie satellite can be put into 3-unit satellite or a 16-unit satellite. So it gives us a bit of a custom built, default built satellite, and it gives us more flexibility. The most important thing in this market, of course, is flight heritage. All the subsystems that go in our satellites are flight proven, and we do not put any unflight proven hardware because you can't really go to space and try and fix it. So now let's break down the architecture of the satellite itself. I'll briefly describe what subsystems are included in the platform and their functionalities. So to start with, firstly we have the onboard computer. We call it flight computer, or FC for short. It is responsible for so-called script engine. It allows us to have, as I previously mentioned, the autonomy. So the tasks that we upload to the satellites can run automatically over a specific region or a specific time. Also, the flight computer hosts the attitude determination and control software. So attitude and determination software allows us to know the satellite's orientation and allows us to point it. So imagine like parking a car, right? So if you want to park it, you have to see where you're parking, or unless it's going to be very, very difficult or impossible, actually. So for knowing our attitude, we are using sensors. So particularly for the Charlie mission, we are using a suite of 6 sun sensors, a star tracker, and a gyroscope. So a sun sensors, as they stand in the name, they basically measure the angle between the sun and the satellite. And for higher precision, we also include a star tracker. A star tracker is a 1,000-year-old, well, not a technology, but an instrument that basically sailors use to navigate through the stars. So having a star tracker together with gyroscopes allows us to have a good precision that is required for this mission. Of course, now we know our attitude, but we still need to point the satellite, so that is done through actuators. So we have a suite of magnet torquers and reaction wheels. So to start with magnet torquers, they are very simple. It's basically a coil wrapped with a wire. It would, can't remember really the count now, but you basically run the current through the wire, which creates a magnetic field, and that magnetic field interfaces with the Earth magnetic field and thus creates a torque. The magnet torquers are used for satellite detumbling. Unfortunately, we didn't see it today, but if you keep your eyes open tomorrow, you can see once the satellites are deployed, they start tumbling, and you don't really want to do that. So the reaction wheels actually detumble the satellite, so they stop the spinning motion. Reaction wheels, quite simple. They're electrically powered wheels that rotate the mass. And if you spin the reaction wheel, it basically creates a torque on the opposite direction, and thus allows us to have a 3-axis control. So basically pitch, yaw, and roll. Now, of course, we need to somehow translate all the data that, for example, the Charlie payload has gathered to the ground. So we have communication systems. So we use 2 communication systems, so UHF radios and S-band radios. The difference between those is, of course, the frequency that they work on, and of course the data rates. The data rates on the UHF radios are quite low. That's why in the Charlie satellite we have upgraded the S-band radio to have almost 200 times faster data rates, because the Charlie satellite is generating quite a lot of data. Other subsystem that we have is so-called payload controllers. Actually, in this satellite we have 2 payload controllers. For redundancy reasons, if one of the payload controllers fails, we still have the second option and the mission can continue without any issues. So the payload controller, quite simply, is basically an interface between the Charlie's payload and NanoAvionics, or the satellite's avionics, basically. So the payload can ask any sort of data from the onboard subsystems if it needs, ADCS telemetry, or anything else. Of course, to power all of these subsystems, we need power, same as the car battery needs power to start your car. And the only way, well, one of the ways to get the power is, of course, sun. So we use solar panels. As you can see here, Charlie has single deployable solar panels. So we use the sun power to charge the onboard batteries, which are inside the satellite, or directly supply the power to all onboard avionics. Other thing for this mission that we did quite interestingly, you can see here, maybe it's hard to see, but you here have the deployable solar panels, but also on this end you have deployable S-band patch antennas. So we have it was because we do have 2 S-band antennas, actually 4. So it was challenging to place them on a single face of the satellite. So our engineers did an amazing job of thinking of deploying those satellites. So you have quite a few of deployments in the satellite. Of course, in other missions, not in Charlie, but the satellites can have a propulsion system which allows the satellite to change its orbit, to go up or down, to meet ESA space debris requirements. If you are at higher altitudes, you need to deorbit within 25 years. So propulsion systems come in handy as well. But as I said, orbital lifetime of Charlie mission is 5 years, and we do not foresee any orbital changes. So this version does not have a propulsion system. And as typically, Gilles, you have always something to add.
I guess you nailed it more or less, but there was one small point I want to add, that in this industry is very, very important one thing, that everything you put in satellite should be flight proven. So more flight proven things you have in the spacecraft, higher reliability you have. So usually in our spacecrafts, in our design, we reuse, as you mentioned before, that we use the same bus more or less in every mission. So one of the things we do, we always try to reuse as much as possible, and all of the buses, all generations are using only flight proven components. And then just another maybe small note, if there is still anyone joining us in this live stream, we wanted to see Falcon 9 lifting off today, but due to bad weather conditions, it was postponed and we could not witness the Charlie deployment. So we're continuing with some questions to our colleagues and customers from Aurora Insight, just to learn more about their business and also uncover a few things from NanoAvionics side. So I guess we can continue.
Yep, so I actually have a question. So as I have described the 6U satellite, so a question to Aurora's team. You know, as they say in Texas, the bigger the better. So was there, I don't know, maybe an idea to have a bigger satellite with bigger antennas, with more surface area, or maybe on contrary, maybe you were trying to fit everything into, you know, maybe a 3-unit satellite. So why the nano satellite and why 6U in particular?
Yeah, we don't actually have any team members in Texas, unfortunately, although Jen is from there, so I'm sure she appreciated that. Nano satellites really have allowed us to accelerate our design cycle and decrease the time from initial concept to receiving actual live data from orbit. As Gus mentioned earlier, we successfully launched our Alpha satellite as an initial proof of concept, and that was 3U in size with a single antenna. But due to the 6U satellite size, we've been able to increase our sensor capabilities and actually go to 3 antennas. The extra 2 antennas are for dedicated C-band and Ka-band collections. And then by integrating with the NanoAvionics satellite bus, as you mentioned, there are several redundancies, and we'll also get higher telemetry accuracy, which will really, the redundancies will really mitigate the risks that you see in any satellite system.
Okay. I also have, Gilles, if you may, have a follow-up question. So in the future, because as you said, the 3U, you had a single antenna. Here in 6U, you have 3 antennas. So in the future, are you thinking about bigger satellites for, you know, a higher number of antennas and different radio frequency spectrums?
I guess that was for Josiah.
Yeah, that was for Josiah.
We'll see what we get from these 2 that we're about to launch, Charlie and Bravo, and we'll make design decisions from there. But we're really excited by the amount of data we'll be able to get from these and the new frequency bands.
Okay, thank you, Josiah. Also, I have a question. So who is these radio frequencies, well, the measurement of these radio frequency spectrums helping? I mean, will it help, for example, Gilles or help me, or is it orientated to like bigger businesses and industries? And why is it so important? And as Jennifer mentioned, it is a finite resource.
Yeah, that's right. RF spectrum is finite. It's licensed and allocated for by national spectrum regulators. And as Jennifer mentioned, the auction that recently concluded in the US for almost $81 billion just shows how scarce spectrum actually is. So our measurements from space, they give our customers the data to understand the global wireless ecosystem. They can compare deployment strategies from country to country, and we can help target our Aurora's ground and airborne operations. From space, we can see massive disparities in access to communications technology, the impact of national regulations, and which countries and states are investing to connect their populations. We can see where new investments are needed and where it's likely to occur soon. We can see new networks that are just coming online and that will impact the economy around them. Also, RF spectrum measurements can help a number of players throughout the space and wireless ecosystem. For example, before a satellite is launched, even as it's being designed, we can provide a detailed assessment of the RF environment in low Earth orbit, or LEO, to understand if there are any terrestrial networks that may raise the on-orbit noise floor or potentially interfere with existing operations. If an on-orbit if an on-orbit satellite does experience interference or degraded service, we can take very targeted collections to understand the interference signals and where the likely source of interference is coming from. We can also track the development of mobile networks, for example, 5G networks, by measuring the change in power over a given time period. You can think of it like an orbital drive test. And these are just a few of the potential use cases, and we're excited to learn about the potential uses from our partners and customers.
Okay, I think I'm out. Gilles, anything on your side?
No, I think it's clear we can move forward.
Okay, so let's continue with other questions that I have. So these results that you will get from space, basically, how are they important and how can they be combined with the land-based and airborne measurements? That's probably a question to Gus.
Yeah, so a majority of the radio frequencies transmissions that we're interested on Earth aren't actually intended to travel all that far. So they're typically very faint by the time they reach space orbit. This means that in order to receive these faint signals, we have to include a radio frequency receiver on board the satellite that's extremely sensitive. is a major driver in the development of the sensors that we've included on our satellites. The receiver that we've included is not only extremely sensitive, it's been designed to be able to listen to a wide range of frequencies through a number of different antennas that we've included on board the satellite. Charlie has 3 different antennas on board, and each of them have different either gain characteristics or directionality and different frequencies over which they listen to. There's been a number of recent advances in miniaturizing both the electronics and antennas that are necessary to do this. And this has enabled us to realize sensors that fit our needs while still being small enough to be included on these buses.
Okay, thank you. Gilles, if you may, another question from me.
No, I guess I will continue. I don't allow you to ask no more questions.
Too technical, right?
What we just hear, that basically miniaturization is helping to drive and achieve this mission. Basically the evolution of all the technical details what we can use in the spacecraft. And this brings us to the new space. Brent, could you comment on this development and what you saw in the past years?
Yeah, absolutely. It's been an interesting ride since way back when I come from big space, big U.S. space, and from Honeywell Space and Defense, big and classified satellites where everything was large monolithic programs, whether for NASA or DoD or big commercial ones like Worldview and such. We all knew small sats were coming, CubeSats and things. Have been going to small sat conference for over 2 decades, and everybody knew it was coming, but they didn't know when it was going to be made practical instead of institutional. So the smaller you can make something, the cheaper it is to get up into space. It's, launch is typically half the cost of things. So going smaller and making it subscribe to a standard, to CubeSat standards, made it easy to compartmentalize and put deployers on and get them integrated into satellites, launch vehicles faster and faster, make them even more cost effective and potential faster and faster cadences for all the launch vehicles that offer rides to nanosats and stuff. But it's been very interesting. First, they were just institutional training for universities and people to get up there. They often had to design their own hardware and equipment and computers to use, but now there's a very healthy biosphere for subsystems and buses and things like that. And now they're focusing on missions and payloads instead of the making the subsystems and things like that. With the advent of faster computing that uses less power, and instruments and optics that can be shrunk down to size to fit in these, has really enabled the business. And people have moved from, like I said, the institutional use of CubeSats for training to actually closing business cases or being able to get up smaller instruments and things like that. It's even though CubeSats and nanosats don't have the apertures and the big power levels that the big monolithic satellites are, they have advantages if you can take advantage of them, and they bring things that you don't get from large monolithic programs. For example, it's lower cost, of course, is the most obvious for everybody. And the ability to be, what they bring is resilience also, because you can put up a couple. If you lost one in a launch failure or this or that, you can put them up. If you want to put up a bunch, you can survive a certain failure rate on orbit. And your revisits, if you're doing Earth observation or sensing from a group of satellites to geolocate, things like that, revisit times. The interesting thing that most people don't acknowledge about CubeSats and nanosats is the cadence of technology, is that you can put these things up in a quicker cadence than you can large monolithic satellites, so that by the time you've got something up there and operating, it's not already obsolete, because it's 5 years old technology. Plus, the actual application that the satellite is being used for can redevelop and improve whatever payload they're working on in a faster cadence. So technology, you're able to take advantage of technology faster and quicker in the commercial world to apply these to bring that new capability quicker and faster to orbit. The applications for CubeSats were thought pretty limited at first, but probably the biggest surprises are, doing useful Earth observation, selling commercial data to NOAA and such for like radio occultation for improving weather. After they've done some demonstration systems, they don't have commercial companies that provide that. There's SAR data that's being provided commercially. It goes into not quite into the CubeSat area, but it's still working its way down into the smaller areas, which would never been thought with the aperture and power demands needed. And then finally, with Aurora Insight, it's been a great evolution to watch. And even though 2 decades ago we knew this was going to kick off and be useful for real commercial, civil, and DoD purposes, it's finally a great honor to be a part of it, seeing it come through and work with a company like Aurora Insight.
Thank you, Brent. I guess I would like then take from this stage to another round of questions, and then I guess it leads to another question for Josiah, because now we know that you will use space-based infrastructure to monitor the networks, and then can you elaborate a bit more? How does your service and approach differs from the standard means of network testing and how it works?
Yeah, I think the main difference is that we're covering a very large area from this small satellite. And so we can put together a near real-time picture of the global RF spectrum environment very rapidly as our satellite orbits the globe. That enables companies or potential customers to really have the whole picture when it comes to what's going on in the global RF environment and how networks are expanding and changing.
All right, thank you. Then maybe someone can explain me. I guess guest is always the right choice to explain some things. As far as you know, you're also doing the airborne measurements of the same of frequencies and networks. And is there any added value in mixing up both space and airborne?
Yeah, there's a lot of value to the way Aurora Insight has approached our efforts. The genesis of the company was thinking about doing this work from space, but as we did tests in the air and calibrated our measurements on the ground, we learned that multi-scale data from all regimes of collection, from space to the air to ground, even fixed sensors that sit on the ground and operate without moving, can be valuable to our customers. And so we at Aurora Insight have taken this approach of multi-scale data and combining it to provide a different set of insights for different customers, or combining them for a single customer. Space data, as we've mentioned, allows us to see the entire globe all at once and provides great context for more focused measurements that we might have on a regional or a local scale, or even a very, very small scale. And so, everybody that uses their cell phone knows that there are dead zones in very small locations. So we want to be able to understand how those arise, not just because of the terrain that we're in, but in the way that the companies have deployed their cellular networks or their IoT networks. And so by taking this view of wide area information and moving it downwards into detail that can be used by the companies and the governments that we support, we can provide an insight that they can't get with an older drive test technique or a space-only technique.
Okay, cool. Thank you. Then, yeah, so that means that we have a lot of data from space. We have airborne data, right? And then I guess it will be kind of famous question if we look at 5G, right? Or any other novel questions. As I mentioned before, some people are afraid, some people don't understand. But is there any advantages your service offer for future developments of such new networks?
So we really are doing things in a different way, as Gus was pointing out. We are measuring the radio frequency spectrum from land, from air, and from satellites. Not only do we have this different approach of these multiple regimes, but we also have a different approach in our sensors. Our sensors are sensing all technologies, all frequencies, all operators and standards. And so what we're able to do, especially for 5G, is first of all, we can map how the radio frequency spectrum is being used. And so from this, we can watch all over the world how 5G is being deployed. So the growth of 5G and 5G infrastructure. And then with our other regimes where we collect data, ground and air, we can actually map these 5G networks. We can see how they are rolling out, how they're being deployed, where they're being deployed, and what frequencies they're being deployed on. As you mentioned, there are some safety concerns, especially related to millimeter wave. And so we can actually measure those signals and show what signal levels are present on the ground. So for 5G, we can help with the measurement of radio frequency spectrum. We can help our clients predict and plan and optimize their radio frequency networks at what's called low band, mid band, and high band for 5G, and ultimately create a better 5G solution that's much more effectively deployed with lower capital expenses and better performance overall.
All right, thank you. I guess we're getting towards the end of our Q&A session. I have one last point I would like to discuss. Is there any specific services that Aurora Insight team is excited about that they will help those services to come into the reality for our community?
Yeah, so Aurora Insight is, we're providing actionable data and insights to accelerate the growth and innovation for faster, more ubiquitous wireless services for all. For example, as Jennifer mentioned, the deployment of 5G and future Gs, LEO mega constellations that are providing low latency satellite internet, especially targeting rural areas, and also satellite enabled IoT devices and more. And we're ready to work with customers throughout the wireless ecosystem, both in space and terrestrially, and to support their missions.
Welcome back. So I hope you enjoyed the Q&A session from yesterday and you learned quite a bit about our specifics, both NanoAvionics and our colleagues from Aurora Insight. And it's now about the time to join the live stream of SpaceX to see the deployment itself. So once again, fingers crossed, and I hope we get the successful results.
Space applications let us monitor and forecast our environment, map the most remote regions, connect unconnected ones, and stream data to homes everywhere. Yet the new space revolution, driven by cost-efficient miniaturized satellites, is distributing the benefits of space access to more industries and countries than ever before. NanoAvionics is pioneering this future with their Nanosatellite technology.
First of all, we started to work with one unit, so 10 by 10 centimeters cubes, but we suddenly realized that those are a bit too small to satisfy our demanding customers. And we started to think how we can get more onboard resources, how we can make more powerful satellites. And we came up with the idea that we have to commercialize 6 units.
Small satellites once relied upon bespoke designs. One-off purchases and qualifications increased costs and lead times. NanoAvionics applied modern industrial principles to nanosatellite design.
We decided to commercialize, to industrialize, and to standardize our products in order to make them cheaper, in order to make them more reliable, in order to make them more repeatable.
NanoAvionics M6P is the first pre-configured nanosatellite bus.
On screen right now is a view of the second stage MVAC engine. We are waiting to relight that engine for the second and final burn. This burn will be a quick one, lasting only 2 seconds. And we're expecting that burn to start in just a few seconds here. And if we don't have footage of it, we should be able to get confirmation over the nets. And there is second engine startup and then cut off. Now we're waiting for confirmation of a good orbit on that second stage.
Nominal payload orbit insertion.
And there's the call out that we want. That is a confirmation of a good orbit. Next up will be the deployment of our 133 spacecraft on board the mission, which will occur over an 18-minute period. And as a reminder, today's mission is the first dedicated small-sat rideshare program mission. We created this program to provide small satellite operators with regularly scheduled rides on board Falcon 9, Falcon Heavy, and in the not-too-distant future, Starship as well. These missions offer competitive pricing to our customers, as well as increased flight opportunities and flexibility. As part of this program, we're also offering traditional rideshare opportunities on existing low Earth orbit missions and on SpaceX's Starlink missions, which provide launch opportunities about once a month. The first of those deployments should be happening around the T+ 58-minute and 30-second mark. There's a view of the Transporter-1 payload containing all 143 spacecraft. For today's ride shares, there are 11 ports on our payload adapter responsible for sending 133 spacecraft plus our 10 Starlink satellites into orbit. Some of these ports will have multiple deployments. For these, over the countdown nets, we'll hear callouts for when the deployment sequence has begun and another callout for when the deployment sequence has completed. There are also then a handful of ports that will deploy only once, and we'll try to let you know who the customer is for each deployment, along with how many spacecraft are being sent into space. We're just over a minute away from the first set of deployments. Due to the nature of the payload stack, we will not have visuals for every deployment, but we do hope to catch most of them with our 2-camera views. It's also worth noting that we will lose access to ground station coverage for a short period during the 18-minute deployment sequence, and when we reach that point, we'll let you know over the webcast. First up, the deployment sequences for port C4 and C1 will be initiated at the T+ 58-minute and 30-second mark. On port C4, there are 36 Planet SuperDoves, and then there are 17 spacecraft aboard Kepler's port on port C1. And we're hoping to get
Ports C4 and C1 deployment sequences initiated.
Those callouts. The deployment sequence has started for 36 of Planet SuperDoves on port C4, as well as the 17 spacecraft aboard Kepler's port on C1. We're expecting these deployments to conclude about 11 minutes from now. In just a few seconds, we should be starting up the deployment for our customer Maverick, which contains 3 CubeSats for NASA's Small Spacecraft Technology Program's VR3X mission. It's going to be deploying from the aft end fuel dome, which essentially is a small platform mounted on the back end of the second stage fuel dome, right above the MVAC engine.
Aft-end payload deployed.
And there you heard the callouts. 3 CubeSats aboard Maverick's Mercury dispenser have deployed. These are for NASA's Small Spacecraft Technologies Program VR3X mission. The next call out will be to start deployment sequence for our customer NanoRacks around the T+ 1 hour and 8 minute mark. And while we wait for this deployment sequence to begin, we're going to leave you with views of the deployments for Planet and Kepler. And we'll see you back here at the T+ 1 hour and 7 minute mark.
Also signal reef expected.
Welcome back to the webcast for Transporter-1, SpaceX's first dedicated smallsat rideshare program mission. On board this mission are 143 spacecraft, the most spacecraft ever deployed on a single mission. If you're just joining us, Falcon 9 had an on-time liftoff at 10 a.m. Eastern from Cape Canaveral Space Force Station. It followed a nominal trajectory after liftoff. The first stage landed for the 5th time on our drone ship, Of Course I Still Love You, and our second stage had 2 successful engine burns. So far, the deployment sequence has begun for 36 of Planet's CubeSats, as well as the 17 spacecraft aboard Kepler's port. If you're looking closely at the left half of your screen, you should see them in the background being deployed from the payload. We're expecting those to be completed around the T plus 1 hour and 9 minute mark. We've also deployed 3 CubeSats for our customer Maverick. We're now waiting to hear that the deployment sequence has started from port C3 for the 9 spacecraft for NanoRac's EAR-1 mission. And while we're waiting for that call out, the white dot on the left-hand side of your screen, that is the moon. Some pretty cool shots of the moon there. And there goes another satellite. Again, we're waiting for confirmation from the team for the 9 spacecraft for NanoRac's
deployment sequence initiated.
EAR-1 mission. And there's the confirmation for the 9 spacecraft. We're expecting to get confirmation that these have completed deployment in about 8 minutes from now once we pass through our ground station blackout period, so stay tuned for that.
Also signal Bangalore as expected.
Next up, we're expecting to get the confirmation that the 36 of Planet's Super Doves have deployed, as well as the 17 spacecraft aboard Kepler's port. And we did get that call out. So far, we've successfully deployed 56 of our 133 smallsat rideshares today. 9 spacecrafts have started their deployment sequence and should wrap up in the next few minutes, leaving another 68 still yet to be initiated. We've now entered that blackout period I mentioned earlier, which means we lose camera views and telemetry. During this time, we are expecting quite a bit of activity, but we won't get confirmation of successful deployments until we regain ground station connectivity around the T plus 1 hour and 15 minute mark. Here's a preview of what will be happening until we regain that connectivity. 9 spacecraft for NanoRacks will complete their deployment sequence. The first of 2 ports for our customer ExoLaunch will start and then finish deploying from port B3. Their second port, B2, will also begin its deploy sequence, but won't be completed until approximately T plus 1 hour and 16 minutes. ExoLaunch has a total of 30 spacecraft on today's mission. From there, 2 spacecraft will deploy for our customer Capella from 2 separate ports. And lastly, Spaceflight Incorporated customer IQPS's satellite will also separate. And while we wait to regain access to ground station coverage in a few minutes, sit back and follow along with our animation that shows you where we're at in the mission. We'll see you back here at the T plus 1 hour and 15 minute mark. and welcome back once again to the Transporter-1 mission. We're in the middle of deploying 133 small sats for commercial and government customers. We're expecting to reconnect with the ground station in just a few seconds, and we should be hearing callouts for the deployments that we didn't see, and these callouts should be happening back-to-back once we reconnect. During this blackout period, we also were able to recover both fairing halves, and they are safely on board our ships. And the callouts for the satellites should be happening around the T+1 hour and 1 hour, 15 minutes, and 50-second mark.
Acquisition of signal, Cordova.
Deployments confirmed on ports C3, B3, C5, B1, and C6. Port B2 deployment sequence initiated and confirmed.
So we did get some confirmations. We should have some more callouts happening in just a few seconds here, and I'll summarize once all of the callouts are done.
Port A4 deployment confirmed. Port A2 deployment confirmed. Port B2 deployment sequence complete.
It sounds like we've gotten all the callouts. I'm going to go ahead and recap all of the different ports. So from port C3, the NanoAvionics EAR-1 mission's 9 payloads have deployed. From port B3 and B2, the ExoPort-1 spacecraft deployed with 2 ICE-I radar imaging satellites aboard, and ExoPort-2 with 28 spacecraft from the DLR ICE-I NanoAvionics Swarm, and TU Dresden began its deployment. From port C5 and C6, deployed 1 small sat each for our customer Capella. From port B1, the Spaceflight Incorporated customer's IQPS satellite has also deployed. And from port A4, SpaceX Spaceflight Incorporated's Sherpa FX-1 spacecraft has deployed with its 13 spacecraft on board. From port B2, the final small sats for EXO launch have now deployed, making for a total of 30 on today's mission. And from port A2, D-Orbit's Pulse mission with its 20 spacecraft on board has also deployed. And that will conclude the rideshare portion of the mission. With these deployments behind us, we are now going to enter another short coast phase before deploying our 10 Starlink satellites. So sit tight, enjoy the music, and we'll be back at the T+1 hour and 30-minute mark. We'll see you then.
Once again, welcome back to the studio, and we just achieved another great milestone where our satellite Charlie was successfully deployed to its designated orbit. So I cannot say that we won't applaud it once again. We do it again for both teams. Great job, guys. And I will allow Arnold to give a bit of the specifics what's going next to be with this mission.
Yeah, so the next few steps are very important, and they will take a bit of time. So this phase is now called the launch and early operations phase, where we basically verify the satellite itself. So 4 hours after the satellite is deployed from the deployer, it will automatically deploy the antennas and the solar panels. After that, we will have the first pass over our ground stations, where we will try to catch the satellite and gets its health telemetry data. If we catch the satellite and we have the telemetry data, we will analyze it on ground and repeat that for 2 or 3 other passes. Once we verify that the antennas and the solar panels have been deployed successfully, we will move to the stage of verification. So small step by step, we will validate each subsystem by subsystem. So we will check the power generation, power distribution. We will check how the attitude and determination control software is working, so the sensors and actuators. So step by step, we will do this. It can take up to 2 weeks, and then we will move to the payload validation itself. So there are particular scripts for health checking the payload. We will upload those to the satellite. And so once that is done and we get the results that we want, we will go into nominal operations, and we will continue those nominal operations as previously mentioned for 5 long good years.
All right, thank you, Arnoldas. So with this good note, I would like to wrap up our live stream for today. So please follow us and Aurora Insight at social media channels or our websites for more updates. And let's stay in touch for other launches.
Thank you. Bye-bye.
Bye.